Hello everyone and welcome to another recitation video. Today I'm going to solve a few problems from the topic of first law analysis of closed systems. So make sure to check the lecture video if you haven't already. I'll put a link to it up here on the screen and down in the description below. Okay, the first problem is here. We have a piston and cylinder device that has a set of stops. It initially contains 0.3 kilogram of steam at 1 megapascal pressure and a temperature of 400 degrees. We let this system cool down. We are asked to find the compression work for two different cases. Case 1, if the final pressure is 1 megapascal and the final temperature is 250 degrees Celsius, and case 2 for when the final pressure is 500 kilopascal. So let's get to it. Let's first draw a schematic of the problem. So we have a piston and cylinder device like this. So this is the piston, and we have a set of stops here as well, like this. Now initially at state 1, we know that our system has a pressure of 1 megapascals and a temperature of 400 degrees Celsius. For part A, we know that our final state has the same pressure while the temperature is 250 degrees Celsius. Okay? Now this is a constant pressure process until the piston hits the stops, that is. But we are dealing with a constant pressure compression. So pressure remains constant. As you can see, the initial and final pressure are the same, so it's a constant pressure process. Now the boundary work of a constant pressure process is pressure, second volume minus the initial volume, right? Which we can write it as pressure times mass times specific volume at the final state minus the specific volume at the initial state. So all we need to do is find the initial and final specific volumes. Now at state 1, if we check the tables, we'll see, by the way, I will leave a link to steam property tables down in the description below. So if you don't have access to any tables right now, you can always go and download that PDF file. Okay, if we check the tables, we'll see that at the pressure of 1 megapascals, the saturation temperature is 179.88 degrees Celsius. Now our initial temperature is 400. Now because our initial temperature is larger than the saturation temperature at 1 megapascals, we can conclude that at state 1, we are dealing with a superheated steam. Okay, now with that out of the way, we can go check the tables for superheated steam and read the specific volume. That's what we're going to do. You go ahead and check the tables, and you will see that the specific volume of steam at 1 megapascals and 400 degrees Celsius is 0.30661 meters cubed per kilogram. So we found the initial specific volume. Now all we need to do is find the final specific volume. Okay, at final state, again, we have the same pressure, so I can check the final pressure temperature with the saturation temperature again. I can see that the final pressure is still larger than the saturation temperature at 1 megapascal, so we're still superheated at final state. So I can go read the tables for the pressure of 1 megapascals and the temperature of 250 degrees and see that the final specific volume is 0.23275 meters cubed per kilogram. All right, so we got both the initial and final specific volumes, all we need to do is plug in everything that we have into the boundary work equation. All right, so if I do that, I'll get that the boundary work is the pressure 1 megapascals. Now, if we want to get the final unit in kilojoules or kilowatts, if you're dealing with power, it is always good to plug in pressure in the form of kilopascals. So 1 megapascal is 1,000 kilopascals times the mass, which is 0.3, times second specific volume, 0.23275, minus the initial specific volume, 0.30661. And if we do the math, we get that the boundary work is minus 22 kilojoules. Now the minus sign means compression. Okay, for part B, the problem says that our final state has a pressure of 500 kilopascals. And it doesn't say anything else. So what does it mean? It means that we discussed it earlier that if the piston is allowed to go down freely, then the process will be constant pressure. Now that the pressure has dropped, it means that the piston has reached the stops. As in, the piston cannot go lower anymore, so the pressure is dropping. Now, we only know that the final state has a pressure of 500 kilopascals, but we always need two intensive independent properties to pinpoint the state of our system. So what else do we know? Now the problem says that the stops correspond to 60% of the initial volume. That's our key. So specific volume 2 is actually 60% or 0.6 times specific volume 1. Now we can use this. Before going into calculating the boundary work, I want to show this entire process for part B on a PV diagram to give you some perspective. So if this is our PV diagram, during the process, when the piston was going down until reaching the stops, the process was constant pressure. So we started at maybe volume 1 here and a pressure of 1 megapascal up here. So we started something like this, right? Compressing. Until the piston hits the stop, which is this point here, which corresponds to 60% of the initial volume, right? Now, after that, the cooling process happens in a constant volume because the piston cannot move and the volume inside the cylinder is not changing anymore. So the process turns into this until we reach 500 kilopascals, right? Now, if I ask you what is the work during this process, you would check the PV diagram, right? The only portion of the process that is work related is the constant pressure part, this area. Now the boundary work is pressure, mass, specific volume 2 minus a specific volume 1, which we know from the problem is pressure, mass, 0.6 of volume 1 minus volume 1, which will give us minus 0.4 times pressure, mass, specific volume 1. Now I can plug in the numbers that I had from part A for specific volume 1 and get the boundary work. It is minus 0.4 times the pressure, 1,000 kilopascals, times the mass, 0.3, times the specific volume at state 1, which was 0.30661. Now, if you do the math, you get that the boundary work is minus 36 0.8 kilojoules. Again, the minus sign means that we are dealing with a compression. Now the key here is that this entire process had two stages. Stage 1 was a constant pressure compression until the piston hits the stops, and then after that is a cooling process at a constant volume. Now, a constant volume process does not involve any boundary work. That's why we don't include it in our calculations. You can see it on a PV diagram. The constant volume process does not have any area on the curve. The constant pressure one, however, has a rectangle area, which we calculated using the equations that we had. All right, so for part C, the problem asks the temperature at the final state of part B. So we're still at 500 kilopascals and the volume is still 0.6 times the specific volume of initial state. We are asked to find the temperature. So what is T2? So let's get to work. Let's start with the specific volume at the final state. So specific volume 2 is 0.6 times the specific volume initially, which is 0.30661. This will give us 0.18396 meters cubed per kilogram. Now, I have the specific volume and I have the pressure. What I need to do is go check the tables. So I'm going to check the tables at the pressure of 500 kilopascals and read the specific volume for saturated liquid and a specific volume for saturated steam. So the liquid is 0.00193. Specific volume for saturated steam is 0.37483, both in meters cubed per kilogram. Our specific volume is larger than the specific volume of saturated liquid, but smaller than the saturated vapor specific volume. So this means we are inside the saturation dome. It means that we are dealing with a saturated mixture. And so the temperature is the saturation temperature at 500 kilopascals, and that will be, from the tables, 151.8 degrees Celsius. We had two intensive independent properties for state 2. One of them was pressure, the other one was a specific volume. I checked the specific volume with the specific volume for saturated liquid and saturated vapor at the same pressure to see where on that dome we are. Because our specific volume was larger than saturated liquid but smaller than saturated vapor, it showed us that we are inside the dome and we are in saturated mixture zone. And in the saturated mixture zone, temperature is a function of pressure. So you just read the saturation temperature of 500 kilopascals from the table, which is 151.8 degrees Celsius. Okay, problem 2. We have a frictionless piston and cylinder device that it initially has 2 kilograms of nitrogen at 100 kilopascals and 300 degrees Kelvin. Nitrogen is now compressed according to a polytropic equation, which is given here. The final temperature is 360 Kelvin. It asks to calculate the work input during the process. Now, this problem is actually very easy. All you need to do is check the lecture for polytropic processes and find the boundary work equation. So the boundary work equation for a polytropic process is, if the gas is ideal, now we are dealing with nitrogen, and nitrogen is an ideal gas that is given. So we can use the polytropic equation for an ideal gas and say the boundary work is mass of the gas times gas constant, final temperature minus initial temperature, over 1 minus n. For a polytropic process, we have P V to the power of n is equal to a constant, right? Now our problem says P volume to power of 1.4 is equal to a constant. So from this, we conclude that n is 1.4. Okay, we can plug in everything into the equation. So the boundary work will be the mass of nitrogen, 2 kilograms, times the gas constant. Now the gas constant for nitrogen, you can find it from the tables, is 0.296 kilojoules per kilogram Kelvin, times temperature difference is 360 minus 300 Kelvin over 1 minus n, 1 minus 1.4. Do the calculations and we get that the boundary work is minus 88.8 kilojoules. Now again, the minus sign means that we are dealing with a compression. And if you check, the problem also says that the gas is being compressed. So our calculations are correct. Now we did this equation with the knowledge of this equation beforehand, but if you do not have the equation, you can always try to find a boundary work as the integral of pressure d volume. Now here we have a relation between the pressure and the volume in the form of the polytropic equation. You can plug this equation into the integral and then use the ideal gas equation to reach this final form of the equation. But I would suggest to put this in your formula sheet on the day of your exam because it is very easy and convenient to use. Okay, problem 3. We have a piston cylinder that contains 50 kilograms of water at 250 kilopascals and 25 degrees Celsius. Now the cross-section area of the piston is given. We are heating up the system and causing part of the water to evaporate and expand. When the volume of the system reaches 0.2 meters cubed, then the piston reaches a linear spring whose spring constant is 100 kilonewtons per meter. Now we are going to continue heating up the system until the piston rises an additional 20 centimeters. Now we are asked to find the final pressure and temperature, the work done during the process, and also show the process on a PV diagram. So let's start with a schematic of the problem. So this is our piston and cylinder. Initially, there is a spring, a linear spring up here. So initially, the piston is located here and the cross-section area is also given 0.1 meters square. Now during the heating process, the piston starts to rise until it reaches this red position where the volume, the total volume inside the cylinder is 0.2 meters cubed. Then we are going to continue heating up until the piston reaches somewhere here, which is 20 centimeters or 0.2 meters above the red position. Now we are asked to find the final pressure and temperature. The purple state is our initial state, the red state is the second state, and the black state is the third and final state. Now initially, we have the pressure, 250 kilopascals, and the temperature, 25 degrees Celsius. At state 2, which is the red state, or the piston at red location, we still have the same pressure, because if the piston is allowed to expand the move without any friction or without any opposition, the pressure inside remains constant. That is the case from the purple to the red position. Piston can move freely, so the pressure remains constant. We also know that the total volume of state 2 is 0.2 meters cubed. And then we go to state 3, which we basically don't know anything about it. Okay, so for part A, we're asked to find the final pressure and temperature. So what do we know about state 3? What we know is that between 2 and 3, the piston has moved up 20 centimeters. And also we know the force that the spring is applying. Remember that the force of a spring is its constant, the spring constant, in this case 100 kilonewtons per meter, times delta x, or how much the spring has been compressed or elongated. So let's use them. So volume at state 3 is volume of state 2 plus this much, right? That is the area of the piston times 20 centimeters, right? The volume of a cylinder is the area of the base times the height. For our case, if we plug in numbers, volume of state 3 is volume of state 2, which is 0.2 meters cubed, plus 0.1 meters squared times 0.2, the height, 20 centimeters rise of the piston. If you do the calculations, you get that the volume 3 is 0.22 meters cubed. All right, now I have the mass, 50 kilograms of water. I can calculate the specific volume. So the specific volume at state 3 is 0.22 over 50, which will give us 0.0044 meters cubed over kilogram. What about the pressure? Okay, I moved the specific volume at state 3 up here, and now we can continue with the pressure. Pressure at state 3 is actually the pressure at state 2 plus the pressure caused by the force of the spring, which will be the force of a spring over the cross-section area. So that will be pressure at state 2, we know it's 250 kilopascals, plus the force that the spring is applying is 100 kilonewtons per meter times 0.2 meters, which the spring has been compressed, over the cross-section area of the piston, which is 0.1, which will give us 450 kilopascals. So there, I found the pressure at the final state. P3 is 450 kilopascals. Now I have two independent intensive properties, a specific volume of state 3 and the pressure at state 3. I can go and check the tables. So from the table, for the pressure of 450 kilopascals, because I only have the specific volume, I'm going to check the specific volumes of saturated vapor and liquid. So saturated liquid at 450 kilopascals from the tables is 0.01093, and the saturated vapor is 0.41392, both in meters cubed per kilogram. Now, our specific volume is larger than the specific volume of saturated liquid, but is smaller than the saturated vapor, right? So what does it mean? It means that at the state 3, we are dealing with a saturated mixture. When we are in the saturated mixture, temperature is a function of pressure. So the final temperature, T3, is the saturation temperature of 450 kilopascals. And if you check the tables, it will be 147.9 degrees Celsius. So what we did in order to answer part A was to play with the data that we had. We know that the volume at state 3 is the volume at state 2 plus the increase of volume because of the 20 centimeter rise of the piston. So we found the total volume and then used the mass to find the specific volume. For the pressure, we again know that up until state 2, the pressure of the system is 250 kilopascals, right? From 2 to 3, the linear spring kicks in. It produces some sort of force that is following the equation of the force of the spring, K delta X, and force over the cross-section area of the piston is the pressure of the spring. So we add that to the already pressurized system, and we get 450 kilopascal is the total pressure. Now that we have two independent intensive properties, we're going to check the tables. to pinpoint the state of our system. We figured out that because the specific volume is between the saturated liquid and saturated vapor, we are in the mixture zone, and the temperature is the saturation temperature at 450 kilopascals, which is 147.9 degrees Celsius. Now let's move to part B. Okay, part B asks for the work done during the process. Let me first show the entire process on a PV diagram, which will answer the part C for us, but it will give us a perspective on what we are going to do. So if this is our PV diagram, PV, then we have state 1, which is somewhere maybe here. We have a constant pressure process from 1 to 2 up until here, right? So this is 1, this is 0.2. Now from 2 to 3, the spring is active. Now remember, when there is a linear spring involved, pressure has a linear dependency on volume. So from 2 to 3, we are dealing with a line. This is 0.3. The work involved in this entire process is the area under this curve. I'm going to divide it into 2 geometric shapes and find the area of each individually. Now let's focus on the work from state 1 to 2. So the work, or the boundary work, is pressure volume 2 minus volume 1. I already know volume 2. The problem says that it's 0.2 meters cubed. So I just need to find volume 1. So at state 1, if I check the tables, I would see that the saturation temperature for the pressure of 250 is actually 127.4 degrees Celsius, right? Now, because my temperature is smaller than the saturation temperature, I'm dealing with a compressed liquid at state 1. Now, for a compressed liquid, the specific volume is equal to the saturated liquid specific volume at the temperature given, which is 25 degrees Celsius. Now, if you read the tables, you will get that the specific volume 1 is 0.001003 meters cubed per kilogram. Now, volume 1 will be mass times the specific volume, which is 50 times 0.001003, which will give us 0.5015 meters cubed. Okay, so this is the initial volume. Now the boundary work is, as I said, pressure times volume 2 minus volume 1, which will give us pressure is 250 kilopascals times 0.3 minus 0.05015, which is 62.46 kilojoules. Now the positive sign means expansion. So you're expanding, right? The piston is rising. You're expanding. The work is positive. Very good. So I found the area or the work from 1 to 2. We can do the same for 2 to 3. Okay, volume 3 is 0.22 meters cubed. We found it already from part A. Volume 2 is 0.2 meters cubed. The problem already gave us. Pressure 3 is 450 kilopascals, and pressure 2 is 250 kilopascals, right? Okay, so this is 250, this is 450, this is 0.22, and this is 0.2. So what is this area? The area underneath, or the work from 2 to 3, is 1/2 of P3 plus P2 times V3 minus V2. plug in the numbers that we have, we get 7 kilojoules. Again, the positive sign means expansion, and we know that the piston is rising, so we are expanding, everything's all right, and the work from 2 to 3 amounts to 7 kilojoules. So the total work is the work of boundary from 1 to 2 plus the work of boundary from 2 to 3, which is 62.46 plus 7. The total boundary work, or the work that the system does, is 69.46 kilojoules. Problem 4. We have a piston cylinder device containing 0.15 kilogram of air, which is initially at 2 megapascals of pressure and 350 degrees. We are expanding the air isothermally to 500 kilopascals. Then we are going to compress it polytropically with a polytropic exponent of 1.2 to the initial pressure. And then we are going to finally compress it at a constant pressure to initial state. So it's a cycle. Determine the boundary work for each process and the net work of this cycle. Let's have a PV diagram just to give us some perspective of what's going on. This is P, this is V. So we start at state 1, and then isothermally we go to state 2. Then I'm going to compress the gas on a polytropic process to state 3, like this, and then compress it again with constant pressure like this. So this is a cycle. Each individual process has an area underneath the curve. So each individual process has some kind of work, and then the area in between will be the net work. So from 1 to 2 is isothermal. From 2 to 3 is polytropic, and from 3 back to 1 is constant pressure. Boundary work of an isothermal expansion of an ideal gas, we already know the equation for it. So from 1 to 2, the boundary work is pressure 1, volume 1, times the natural log of volume 2 over volume 1. Now we are dealing with an ideal gas, air, so I can plug in MRT1 instead of P1V1. So the boundary work from 1 to 2, isothermal expansion, is mass times the gas constant times the temperature, natural log of specific volume 2 over specific volume 1. Now the reason that I was able to replace volume 2 over volume 1 with a specific volume 2 over a specific volume 1 is that the mass of the system does not change. If the mass does not change, then the ratio of volumes is equal to the ratio of a specific volume. Ideal gas equation states that pressure times the specific volume is R times temperature. So from this, I would say specific volume is RT over pressure, right? I'm going to combine this equation with this equation. So the work from 1 to 2 is mass RT1 natural log of specific volume 2 is RT2 over P2. Specific volume 1 is RT1 over P1, right? Now remember that the process from 1 to 2 is isothermal. It means T1 is equal to T2. So T1 and T2 cancel, gas constants cancel as well, and we end up with the equation in the form of boundary work from 1 to 2 is mass R temperature 1 natural log of P1 over P2. So let's plug in some numbers. Boundary work of the isothermal expansion is 0.15 times gas constant for air is 0.287 kilojoules per kilogram Kelvin. Okay, you can read it from tables. 287 natural log of P1, 2 megapascals, which is 2000 kilopascals, over P2, which is 500 kilopascals. 500. Now, if you do the math, you get that the isothermal expansion work is 37.18 kilojoules. So just to recap, we already knew the equation for the boundary work of an isothermal expansion of an ideal gas. Then we played with the ideal gas equation in order to find the ratio of specific volumes and plugged in numbers and found 37.18 kilojoules of work was done during this process. Okay, let's move on to the process from 2 to 3. It's a polytropic compression. Okay, so the equation is P volume to the power of 1.2 is equal to a constant. This is the equation for the process. Again, remember from problem 2, we already know the equation for this process. We know that the boundary work from 2 to 3 is mass times constant, gas constant, temperature 3 minus temperature 2 over 1 minus n. Now T2 is known because 1 to 2 was isothermal, so T2 is equal to T1. Mass and R are also known, n is also known, T3 is only unknown. We have to find a way to find T3. Now in order to find temperature 3 during a polytropic process, we have to combine the two equations that we have. First is the ideal gas equation, P specific volume is equal to R temperature. And the second is a polytropic process, which says P specific volume to power of n is equal to a constant, right? If you combine these two equations, you will get that temperature 3 is temperature 2 times P3 over P2 to the power of n minus 1 over n. Okay, now this is a very useful and famous equation. As I said, you can reach this equation by playing with the ideal gas and the polytropic equation. If we plug in numbers, T3 is T2. The problem says the T1 was 350 degrees Celsius, and T2, because of the isothermal process, is 350 Celsius. But remember here, you need to plug in things in Kelvin. So 350 degrees Celsius is 623 degrees Kelvin times P3, which is the problem states, is the initial pressure, so 2000 kilopascals, over P2, which is 500 kilopascals, to the power of n minus 1. Now n, the problem states, is 1.2, minus 1 is 0.2 over 1.2. Now you do the calculations, you get that the temperature at the third state is 784.93 Kelvin. Now, keep in mind that I derived this equation to make life easier, okay? You can definitely use these equations in a more traditional way and find the specific volumes first and then plug it back into the ideal gas equation to find the temperature. I didn't want to do that. I just found the final equation and plugged in numbers because I think it's easier, but you can do that as well. Now that we have the temperature at state 3, we can use the work equation up here to find the work. Okay, so let's plug in numbers. The mass is 15.15 kilograms. R is 0.287. Temperature 3 minus temperature 2 is 784.93 minus 623 over 1 minus n, which is 1 minus 1.2. You do the math, we get that the boundary work from 2 to 3 is minus 34.85 kilojoules. Now a minus sign shows compression. And as you can see, 2 to 3 is a compression, so we're good on the sign at least. Now the final process is from 3 to 1, another compression, this time with constant pressure. So the work from 3 to 1 we know is the pressure times volume 1 minus volume 3, or mass times pressure times specific volume 1 minus a specific volume 3. Now we know the mass, we know the pressure, we need to find the specific volumes. In order to find the specific volumes of 1 and 3, we are going to use the ideal gas equation. P specific volume is RT. So for state 1, P1 specific volume 1 is RT1. Okay, now plug in numbers, we get specific volume 1 is R.287 times temperature 1, 623, over pressure 1, 2 megapascals, which is 2000 kilopascals. Now the reason I'm using kilopascals is because R is in kilojoules. Now, if your R, or gas constant, is the unit of kilojoules, then your pressure has to be in kilopascals. Do the math. Specific volume 1 is 0.0894 meters cubed per kilogram. All right. We can do the same thing for state 3. Specific volume 3 is the same, 0.287 times temperature 3, we found it from previous page, 784.93 over 2000. Specific volume 3 is 0.1126 meters cubed per kilogram. Okay, so this is specific volume at state 3. I can plug in both of these back into my equation and find the work. So let's do it. So the work from 3 to 1 is 0.15 times 2000 times volume 1, specific volume 1 was 0.0894 minus 0.1126. Do the math, we get boundary work from 3 to 1 is minus 6.96 kilojoules. Now again, the negative sign means compression. We are dealing with the compression from 3 to 1, so we are good. Finally, the problem asks for the net work of the cycle. So the net work is the summation of all these works. Boundary work from 1 to 2, plus the boundary work from 2 to 3, plus the boundary work from 3 to 1. So plug in numbers. From 1 to 2 was our expansion, 37.18. 2 to 3 was our first compression, minus 34.85. 3 to 1 was our final compression, minus 6.96. Now add these numbers together and we get that the net work of this cycle is minus 4.63 kilojoules. So what does this mean? What does this mean that the net work of a system is negative? It means that this piston and cylinder is not producing work, rather it's consuming work. During these three processes, from 1 to 2, 2 to 3, and 3 to 1, this machine consumed 4.63 kilojoules worth of work. Problem 5. We have 5 kilograms of saturated liquid vapor mixture, so initially it is a mixture. In a piston and cylinder, the pressure is also given, 125 kilopascals. 2 kilograms of water is in the liquid phase, and the rest is in the vapor. So, first things first, total mass is 5 kilograms. Fluid mass is 2 kilograms, right? So it means that the vapor mass is 3 kilograms. So the initial quality is 3 over 5 or 0.6. There, we found the initial quality from the second line of the problem. Heat is transferred to the water, and the piston, which is resting on a set of stops, starts moving when the pressure inside reaches 300 kilopascals. So initial pressure is 125, but the piston does not move until the initial pressure reaches 300 kilopascals. So we have a constant volume process from 125 kilopascals to 300 kilopascals. Then we continue to heat the system up until the final volume has increased 20%. We are asked to find the initial and final temperatures, the mass of liquid water when the piston starts to move, the work, and also show it on a PV diagram. Okay, so we have this piston and cylinder. It has a set of stops like this, and the piston initially is resting on these stops, right? So from the initial pressure of 125 kilopascals to pressure of 300 kilopascals, the entire process is happening at a constant volume because the piston is not moving. So let's divide this entire problem into three states. State 1 is the initial state where we have the pressure of 125 kilopascals. State 2 is when the pressure reaches 300 kilopascals. And state 3 is when the piston has moved so that the final volume is 1.2 times the initial volume. So we have state 1, state 2, and state 3, or the final state. We are asked to find the initial and final temperatures. So let's do it. So for part A, the initial temperature, we have that the pressure is 125 kilopascals. We also know that we have a quality of 0.6. Now, having a quality means that we are in the saturated mixture zone, which means temperature is a function of the pressure. And T1 is going to be the saturation temperature at pressure of 125 kilopascals, which if you check the tables is going to be 105.97 degrees Celsius. So we found the initial temperature, no problem. How about the final state? So what do we know about the final state? We know that its volume is 1.2 times the initial volume. We also know that its pressure is 300 kilopascals. The moment the piston starts to move, pressure remains constant. So P3 is equal to 300 kilopascals. We know that. We also know that specific volume 3 is 1.2 times the specific volume 1. So if I have the specific volume V1, I can find the specific volume at state 3. So in order to find V1, we need to check the tables. Again, the same tables that we found the temperature from. At the pressure of 125 kilopascals, specific volume of saturated liquid and a specific volume of saturated vapor can be found from the table. They are 001048 and 1.3750, both meters cubed per kilogram. Now, the initial quality is 0.6. I can say the specific volume is 1 minus x1 specific volume of saturated liquid plus x1 specific volume of saturated vapor. Plug in the numbers that we have, we get that specific volume 1 is 0.82549192 meters cubed per kilogram. Okay? So this is the specific volume at the initial state. What about the final state? So V3 is 1.2 times V1. Now plug in numbers, we get 1.2 times 0.82549192, which will give us 0.99.5 meters cubed per kilogram. Okay, now we have both the specific volume and the pressure at the final state. We need to use them to see where we are on that dome. So I'm going to check the tables for the pressure of 300 kilopascals and read the specific volume of saturated liquid and the specific volume of saturated vapor. For the pressure of 300 kilopascals, the saturated liquid specific volume is 0.001073, and the saturated vapor is 0.60582. I see that the specific volume at state 3 is larger than the saturated vapor at the pressure of 300 kilopascals. So this means that we are dealing with a superheated. I'm going to show it at the end of the problem. Now that we know that we are dealing with a superheated steam, we can use the tables to find the temperature. Okay, so you go check the tables and you will probably see that the exact number that you have here for a specific volume is not on the table. So what you need to do is to do a linear interpolation. So after doing a linear interpolation, which I did in a previous video, I'm gonna put the link to it down in the description below so you can see how to do it. You will see that the temperature at the final state is 373.6 degrees Celsius. So what we did to pinpoint the state 3 is that first we concluded that because the piston starts to move, the pressure remains constant. Now we know that the pressure at which the piston starts to move is 300 kilopascals. That's how we found the final pressure. Then the problem says that the volume 3 is 20% larger than the initial volume. So volume 3 is 1.2 times the volume 1. We use that to find the specific volume. We check the specific volume at state 3 with the saturated vapor specific volume at pressure 300 kilopascals and figured out that our number is larger. So it means we are in the superheated region, and then we checked the tables, saw that the exact number that we have is not on the table, so we made a linear interpolation and figured out that the final temperature is 373.6 degrees Celsius. Okay, so let's move to part B. Part B asks the mass of liquid water when the piston first starts to move. So we are dealing with state 2. So what do we know about state 2? We know that state 2 has the pressure of 300 kilopascals, and we know that the specific volume of state 2 is equal to the specific volume of state 1 because the entire process from 1 to 2 was a constant volume 1, right? Okay, so let's check the tables again. We already have the numbers from part A at pressure of 300 kilopascals. The specific volume of saturated liquid and saturated vapor are given. For liquid, it's 0.001073, and for vapor, it's 0.60582, both in meters cubed per kilogram. Also, specific volume 2 is equal to specific volume 1, which we already know from previous pages, is 0.82549192. Okay, now if we compare the numbers that we have, we get that specific volume 2 is larger than specific volume of saturated vapor. See, 0.8 is larger than 0.6. So at state 2, we are dealing with a superheated steam. Now, as the state is superheated, it means zero liquid is present. So in order to answer the mass of the liquid water when the piston starts to move, the answer is there is no liquid form. Everything is in steam. Okay, part C. Part C asks for the work done during the process. Now, process from 1 to 2 is constant volume, so no work involved. So no work from 1 to 2. Process from 2 to 3 is a constant pressure. So 2 to 3 is constant pressure and there is some work involved. The work from 2 to 3 is pressure times mass times specific volume of state 3 minus the specific volume of state 2. It's just a matter of plugging numbers. So work from 2 to 3 is the pressure, which is 300 kilopascals, times the mass, 5 kilograms, times the specific volume, 3. We have it from previous pages. It's 0.9905 minus specific volume of state 2, We also have it from last page. It's 0.82549192. And if you do the calculations, you get that the work from 2 to 3 is 247.65 kilojoules. Now finally, for part D, we are asked to show the entire process on a PV diagram. So this is P and this is V. So to get a better feeling, I'm going to plot the saturation dome here as well. The system starts at somewhere here in the saturation dome. Remember, we had an initial quality. And then it goes through a constant volume process to here. So this is state 1, this is state 2. The process from 1 to 2 was constant volume. And then expands with a constant pressure to state 3. Now, as you can see, state 1 is saturated mixture. State 2 falls outside the dome on the right-hand side, so it's superheated. And then the constant pressure expansion goes deeper into the superheated region. So this is the PV diagram of problem 5. Problem 6. We have 5 kilograms of saturated liquid vapor mixture of water at 100 kilopascals. Now initially, 3/4 of the mass is in the liquid phase. An electric resistor placed inside the tank is connected to a 110 volt source, and a current of 8 amperes flows through the resistor. It asks how long it will take to vaporize all the liquid inside the tank. We also need to show the process on a TV diagram, not the PV, the TV diagram. Okay, so at state 1, we are dealing with 100 kilopascals of pressure and also saturated mixture. We already have the quality. The problem states that 3/4 of the mass is in the liquid phase, right? So only a quarter is in vapor. So quality, the initial state, is 25% or 0.25. The final state, we know that the volume is not changing because we are talking about a rigid tank. The volume, the final state, is equal to the volume initial state, and the entire water has vaporized. So we are dealing with the saturated vapor state. Okay, so these are the things that we know about the second state. Now, this problem is a bit different from the problems that we dealt with so far. We are talking about some sort of energy interaction in the form of electric power or electric energy coming inside the system. This gives you a clue that we need to analyze this problem using the first law equation. So let's do that. So we know that the net heat minus the net work is the change of energy of the system. Now, the system that we are working with is a rigid tank. There is a resistor inside. The problem specifically states that this tank is insulated. So no heat can come in or out of the system. Now, this tank is not moving, it's not changing elevation, so it's a safe bet to assume that the change of energy of the system is actually the change of internal energy. Okay, so we get that minus W net is equal to the change of internal energy. Now, W net is defined as work going out of the system minus work coming into the system. Now here, the system is not doing work in any way, so work going out is 0. The work coming into the system is the 110 volt resistor. So work in is going to be the electric work. Plug everything back into our equation, we get that the electric work is equal to the change of internal energy of our system, which is mass of the system, internal energy of the final state, minus internal energy of the initial state. We need to find the internal energy initial state and the internal energy of the final state in order to be able to use this equation. So let's get to that. So what do we know about state 1? We already know that the pressure is 100 kilopascals and the quality is 25%. We are looking for U. So we need to check the tables and read the internal energy of saturated liquid and the internal energy of saturated vapor, or the difference, U of Fg, at the pressure of 100 kilopascals. So let's do that. I'm going to check the tables at the pressure of 100 kilopascals and see that U of F is 417.4, and U of Fg, which is the difference between U of G and U of F, is 2088.2, both in kilojoules per kilogram. Okay, U1 is going to be U of F plus x1 U of Fg. So plug in numbers, I get U1 is 939.45. So I found U1. How about state 2? At state 2, I know that the specific volume has not changed because no mass has entered or exited the system and the volume has kept constant, so specific volume is the same. So specific volume is equal to a specific volume of the initial state, and we are dealing with a saturated vapor, right? So let's get to that. First, we need to find the specific volume at state 1. So let's go back to the tables and read the specific volume of saturated liquid and vapor for pressure of 100 kilopascals. Again, tables, we get specific volume of saturated liquid is 0.001043, and the vapor is 1.6941, both in meters cubed per kilogram. Now I'm going to use the equation with the quality to say specific volume 1 is 1 minus x1 V of F plus x1 V of G. If we plug in numbers, the ones that we have from the table, and 25% for x1, we get that the specific volume initially is 0.4243 meters cubed per kilogram. Okay, now we know specific volume 2 is equal to specific volume 1, which is 0.4243 meters cubed per kilogram. Okay, so the other point about state 2 is that it's saturated vapor. So this is actually V of G for state 2, okay? So we need to go to the tables and check at what pressure or at what temperature the saturated vapor specific volume is equal to 0.4243. Now if you do that, you will see that you cannot find the exact number that you're looking for. So we need to do a linear interpolation. Again, if you are not familiar with linear interpolation, I've done it in a previous video in detail, so I'll put the link in the description below. Go check that video to see how to do a linear interpolation within the table, the property tables. Now, you would see that the specific volume of saturated vapor that we have falls between the values of two pressures, 400 kilopascals and 450 kilopascals, right? Now, if we do the linear interpolation, you will see that the pressure that we're looking for is actually 439.3 kilopascals, okay? But the pressure was not the one that we were looking for. We are actually looking for the internal energy at state 2. Again, state 2 is saturated vapor. So we want to find the UG of this newfound pressure. In order to do that, we again need to do a linear interpolation between the UG of 400 kilopascals and the UG of 450 kilopascals, okay, for the value of pressure 439.3 kilopascals. Now, if you do that, again, a linear interpolation, you get that U2 which is the UG at 439.3 kilopascals, is equal to 2,556.24 kilojoules per kilogram. Now we have both internal energies at initial and final state. We can jump back to our first law equation. So the electric work was equal to the mass times U2 minus U1. Now what is the electric work? Electric work is electric power, which is voltage times amperage times time times delta T. Okay, so this is voltage, this is amperage, and this is just time. So let's plug everything into the equation. So the voltage is 110 volts, amperage is 8 amperes. We are looking for the time, is equal to the mass of our system is 5 kilograms times U2, we found it in the previous page, is 2,556.24 minus U1 is 939.45. One thing you need to pay attention to is the units. This equation on the left-hand side gives you work in the form of joules. This equation on this side, on the right-hand side, gives you kilojoules. So we need to do something about it. That's why I'm going to convert it to joules using 10 to the power of 3 on the right-hand side. Now the right-hand side is giving you joules. Now do the calculations for delta T. We get that the time is 9,186.33 seconds, which is about 153.1 minutes, which is about 2 hours and 33 minutes. So just using this electric resistor, it roughly takes 2 hours and 30 minutes or 2.5 hours to evaporate all the water inside this tank. So the key part of this problem and this solution were the keywords inside the problem. First, the insulated word here means that there is no Q involved, so Q net will be 0. And then the rigid tank shows that the volume remains constant. Okay, problem 7. We have an insulated tank that is divided into 2 parts by a partition. One part of the tank contains 2.5 kilograms of compressed liquid water at 60 degrees and 600 kilopascals, and the other part is evacuated or empty. The partition is now removed and the water expands to fill the entire tank. Determine the final temperature of the water and the volume of the tank for a final pressure of 10 kilopascals. We have this tank. There is a partition in the middle. This side we have 60-degree water at 600 kilopascals, and the other side is empty. Again, we have a keyword insulated, meaning no heat is transferred from or to this tank. And also, when the partition is removed and the water expands, this is a classic example of expanding against vacuum. We discussed this in the lecture. Again, check the video if you haven't already. When a system expands against vacuum, there is no work involved. Just to wrap things up, insulated means that the Q net is going to be 0. And expansion against vacuum means there is no boundary work. Okay? And since there is no other type of work involved in the problem, we can assume that the net work is also 0. So let's write down the first law equation. Q net minus W net is equal to the change of energy of the system, right? Which in the case of this tank, we are okay to neglect the kinetic and potential energies. This reduces to the change of internal energy. Because of the insulation, Q is 0. Because of the expansion against vacuum, W is 0. And we end up with internal energy of the second, the final state, is equal to the internal energy, the initial state. Now with this in hand, let's get to the problem. At state 1, we have 600 kilopascals and 60 degrees Celsius. Now, if we check the tables, we get that we are in the compressed liquid state, because our temperature, 60 degrees, is way smaller than the saturation temperature at 600 kilopascals. Now, use the newly found information to find the internal energy at initial state, which is equal to the saturated liquid internal energy at the temperature of 60 degrees, which again, if we check the tables, is 251.16 kilojoules per kilogram. So if I plug in U1 here, I get that U2 is 251.16 kilojoules per kilogram as well. Okay, what else do I know? I know that at the final state, pressure is 10 kilopascals, right? The problem says so. Now I have two independent intensive properties, and I can use them to find the other properties, such as the temperature. So I'm going to check the tables for the pressure of 10 kilopascals and read saturated liquid and saturated vapor internal energies. So U of F, if I check the table, U of F at 10 kilopascals is 191.79, and U of G is 2,437.2, both in kilojoules per kilogram. Now, if we compare our U to these two extremes, we get that U2 is larger than UF, smaller than UG. This means that we are dealing with a saturated mixture. Now, at state 2, we are a saturated mixture, meaning the temperature is a function of pressure. So T at state 2 is the saturation temperature at 10 kilopascals, which if you check the tables is 45.81 degrees Celsius. So I found the final temperature. Now we are looking for the volume of the tank as well. Now the volume of the tank is actually the volume of state 2, which is mass of our water times the specific volume at state 2. So let's get to it. I need to go check the tables again at 10 kilopascals and read the specific volume for saturated liquid and saturated vapor. So for saturated liquid, I'm looking at 00101, and for saturated vapor, I'm looking at 14.67, both in meters cubed per kilogram. And then I can say specific volume 2 is 1 minus x2, because I'm in the saturated mixture, we have F plus x2, we have G. Now what is x2? I need to calculate it first. So in order to calculate x2, I'm going to use the internal energy at state 2. I'm going to use this number. I'm going to say x2 is internal energy 2 minus internal energy of saturated liquid over U of Fg, or the difference between the internal energy of saturated vapor and saturated liquid. Now plug in numbers. We have 251.16 minus 191.79 over 2,245.4, which gives me quality 2 is 0.026 or 2.6%. Okay, now that I have x2, I can plug it into this equation and find volume 2. All right, so specific volume 2 is going to be 1 minus 0.026 times 0.00101 plus 0.026 times 14.67, which will give me specific volume 2 is 0.3824 meters cubed per kilogram. Finally, volume of the tank is equal to volume 2, because at state 2 the entire tank is filled with water, which is equal to mass times specific volume 2, which is 2.5 kilograms times 0.3824. The volume of the tank is 0.956 meters cubed. Okay, so this problem had a few keywords inside the problem description. First, insulation, which should give you an instant data in the form of no heat. Then we have a partition, and on one side of the partition there is vacuum or evacuated. So when the partition is removed, in these cases, all of the cases that one side is vacuum and one side has a system, the expansion doesn't do any work. So these are the two most important parts of this problem. The rest was just using the equations and the tools that we had. Okay, problem 8. We have an insulated piston cylinder device that has 5 liters of saturated liquid water at a constant pressure of 175 kilopascals. Water is steered by a paddle wheel while a current of 8 ampere flows for 45 minutes through a resistor placed in the water. If 1/2 of the liquid is evaporated during this constant pressure process and the paddle wheel work amounts to 400 kilojoules, determine the voltage of the source. So what we have is a piston and cylinder, right? So this is the piston. There is a resistor inside the piston cylinder, and we also have a paddle wheel doing some work. Initially, we have 5 liters. So initially, we have saturated liquid that is given. Pressure is also given, 155 kilopascals. And then at the final state, half of the water has evaporated. Means that 50% is evaporated, 50% is liquid. So the quality is 0.5. And because the process is constant pressure, P2 is still 175 kilopascals. Now we want to see what is the voltage of this resistor. Okay, so let's get to work. The equation that we're going to use is Q net, I'm dropping the net subscript just for simplicity, minus W net is equal to the change of energy of the system. Again, no potential and kinetic energies, so this is the change of internal energy of the system. The problem says insulated, so Q is gone. Work is still there because there is a resistor, there is a paddle wheel, and also this is a constant pressure expansion. So keep that in mind. Is equal to delta U. Now W net is the work that the system is doing, work out, which is the expansion, boundary work, minus W of the paddle wheel, I show it with PW, minus the work of the electric resistor. Now, boundary work is the constant pressure, mass, specific volume 2 minus specific volume 1, right? We already know that. Minus the paddle wheel work, the problem says 400 kilojoules, minus the electric work, which is unknown. Now, if I plug things back into the red problem up there, I get 400 plus the electric work minus P mass V2 minus V1 is the change of internal energy, which is mass U2 minus U1. I'm going to play with this problem a little, with this equation actually. I'm going to move this to the right hand side. I get 400 plus the electric work is equal to mass U2 plus PV2 minus U1 plus PV1, right? Now, by definition, this is enthalpy of the second state. This is the enthalpy of the initial state. So I get 400 plus the electric work is equal to mass change of enthalpies. Now, all I need to do is find the enthalpy at the initial and final state. So let's do it. Okay, at state 1, we know that we are dealing with saturated liquid at 175 kilopascals. So the enthalpy at the initial state is the enthalpy of saturated liquid at set pressure, which if you read from tables is 487.01 kilojoules per kilogram. Now for state 2, because of the saturation mixture and the quality, we need both the H of F and H of Fg at 175 kilopascals. H of F we already know is 487.01. H of Fg is 2213.1, both in kilojoules per kilogram. Now I can use the equation H2 is H of F plus X2 H of Fg. If I plug in numbers, I get H2 is 1593.56 kilojoules per kilogram. So I have H1 and I have H2. I can plug both onto this equation on top. What I get is 400 plus electric work is equal to the mass. Now we know that we have 5 liters of water. 5 liters is 0.005 meters cubed. The specific volume at state 1 is also known. We can read it from the tables. So specific volume 1 is the saturated liquid specific volume, and it is 0.01057 meters cubed per kilogram. I can find the mass from these two. I can say mass is volume divided by specific volume, which is 4.73 kilograms. Okay, volume was 0.005, specific volume was 0.001057, and if you plug these two into this equation, you get that the mass is 4.73 kilograms. So let's continue with the equation below. Plug in mass 4.73 kilograms times H2 1593.56 minus H1 487.01, and we get that the electric work is 4,833.98 kilojoules. But this is not what the problem asks. The problem wants to know the voltage of the electric source. Okay, so we know that electric work is the voltage times amperage times the time that the current is flowing. So I can say, now, one thing that you need to pay attention to, if you want to get the voltage in volts, in ampere in ampere, and time in seconds, then this side of the equation will give you joules, not kilojoules. The number that we have is in kilojoules, so we need to convert it. So we have 4,833.98 times 10 to the power of 3 joules is equal to our unknown voltage times the ampere is 8 times 45 minutes. 45 minutes is 45 times 60 seconds. Do the calculations. and you get that the unknown voltage is 223.8 volts. So this problem involved three different type of works. A paddle wheel work, a kind of mechanical work that was 400 kilojoules, some sort of electric work that we were interested in, and also because it was a constant pressure process, the piston was moving, so we had boundary work involved as well. Now, we could have treated the boundary work individually, but I decided to combine it with the change of internal energy and work with one single change of enthalpy instead of dealing with two separate terms. Okay, problem 9. We have two tanks that are separated by a partition, tanks A and B. Tank A initially contains 2 kilograms of steam at 1 megapascals and 300 degrees Celsius, and tank B contains 3 kilograms of saturated liquid vapor mixture with a vapor mass fraction of 50% at 150 degrees. The partition is now removed and the two sides are allowed to mix until the mechanical and thermal equilibrium are established. Mechanical and thermal equilibrium means that the pressure and temperature reaches a steady number. If the pressure at the final state is 300 kilopascals, it means that the pressure inside the entire tank is 300 kilopascals. Determine the temperature and the quality of steam at the final state and the amount of heat loss from the tank. So what do we have is a tank like this. We have a partition in the middle. This is tank A, this is tank B. Tank A has 2 kilograms, 1 megapascals, and 300 degrees. Part B, or tank B, has 3 kilograms. The quality is 50%, and the temperature is 150 degrees, right? Something that we need to pay attention to is that this problem, I know that there are two different tanks, but the final state where the partition is removed, the entire tank is our system, right? So in order to bypass some confusion and some difficulty with the calculations, I'm going to assume that the system, even at the beginning, is the entirety of the tank. So my system is the combined area of tanks A and B. Why is that important? Because when the partition is removed and these two fluids, these two tanks start to combine, I don't need to concern myself with what happens in the middle, because whatever happens when the partition is removed happens inside my system and so goes into the internal changes. Because it's not crossing the boundaries, these black lines, I do not need to concern myself with it. It will resolve itself when I go into the change of internal energies. Okay, so this is a smart move. Okay, for part A, we're asked to find the final state. So what do we know about the final state? At the final state, we know that the pressure is 300 kilopascals. What else do we know? We know that the volume of state 2 is equal to the volume of tank A plus the volume of tank B. Pressure is 300 kilopascals, all right, but what is the volume? We need to find both the volume of tank A and the volume of tank B. So let's get started. For tank A, initially I had 1 megapascals and 300 degrees steam. Now, if I go check, I will see that, checking the tables, I would see that we are dealing with a superheated steam. So I can read the specific volume from the superheated table at 1 megapascals of pressure and 300 degrees Celsius. If I do, I see that specific volume is 0.25799 meters cubed per kilogram. For tank B, the same. I had 150 degrees Celsius temperature and a quality of 0.5. Because I have a 0.5 quality, I'm sure that we are in a saturated mixture zone, right? So I can use the saturation mixture equation to find a specific volume. So the specific volume of tank B is 1 minus xb V of F plus x of B V of G. I need to read these two numbers from the tables as usual. So for tables at 150 degrees saturated temperature, I get that V of F is 0.001091 and V of G is 0.39248, both in meters cubed per kilogram. And if I plug these into my equation, I get that specific volume of tank B initially was 0.19678 meters cubed per kilogram. So I have the initial volume of tank A, the specific volume of tank A. I have the specific volume of tank B. I can find the volumes right now. Okay, volume A is mass of A times the specific volume of A, which is 2 kilograms times V of A, gives us 0.51598 meters cubed. Volume of tank B is mass of tank B times the specific volume of B, which gives us 0.59.34 meters cubed. Volume 2 is volume A plus volume B. So volume 2 is the sum of these two numbers, which is 1.10632 meters cubed. Now, how about the specific volume 2? Volume is extensive. We need an intensive, which is the specific volume. We need an intensive property. So I'm going to calculate the specific volume at state 2, which will be volume 2 over mass 2. Now, mass 2 is, because the partition is removed, water from A and B have mixed and they have a total mass of A plus mass of B. I'm going to plug in numbers and get that specific volume 2 is 0.221264 meters cubed per kilogram. Okay, now I have pressure and specific volume, two intensive independent properties. I'm going to check the tables at the pressure of 300 kilopascals and read V of F and V of G. V of F is 0.001073. V of G is 0.60582. Our specific volume is larger than V of F, is smaller than V of G. So we are in a saturated mixture at state 2, where temperature and pressure are functions of each other. So the final temperature is going to be the saturation temperature at the pressure of 300 kilopascals. Now we can read that from the tables. It is 133.52 degrees Celsius. But that's not all. The problem also asks for the quality of steam at the final state. It's asking for X2. So X2 is going to be V2 minus V of F over V of G minus V of F. Plug in the numbers that we have, we get that X2 is 0.364 or 36.4%. For part B, we are asked to find the amount of heat lost during the process. Now, we know that Q net minus W net is equal to the change of energy of the system, which in this case, because we can neglect kinetic and potential energy, is the change of internal energies. There is no work crossing the boundaries, there is no expansion or compression, so work is 0. We get that Q, all of the heat transfers in and out of the system, is equal to U2 minus U1. I can play with this equation in the form of what is U2? U2 is mass 2 times internal energy 2. What is U1? This is where the things get a bit interesting. At initial state, this half is tank A, this half is tank B. So initial internal energy is the mass of tank A, internal energy of tank A, plus mass of tank B, internal energy of tank B. I need to find all these three. I need to find U2, U of A, and U of B. So let's get to it. At state 1, we already concluded that we are dealing with superheated steam. So I can read the tables for the pressure of 1 megapascals and 300 degrees Celsius, and read that the internal energy of tank A is 2,793.7 kilojoules per kilogram. So U of A is done. This is actually A. So at B, we are dealing with a mixture, right? XB is 50%. T of B is 150. So I need to go check the tables and read U of F and U of FG at 150 degrees Celsius. So if you do that, you get U of F is 631.66 and U of FG is 1927.4, both in kilojoules per kilogram. U of B is equal to U of F plus XB U of FG. You get that U of B is actually 1595.36 kilojoules per kilogram. So this is U of B, this is U of A, so I have two of my unknowns. I still need to find U2. So at state 2, we have a pressure of 300 kilopascals and a quality of 0.364, right? I can use this to calculate U2. All I need is U of F and U of FG for the pressure of 300 kilopascals. So I go check the tables and read U of F is 561.11, U of FG is 1982.1, and then use the equation U2 is U of F plus X2 U of FG, which gives me U2 is 1282.59 kilojoules per kilogram. Okay, I found U2 as well. I can plug everything back into my equation. Mass 2 is mass A plus mass B, which is 5 kilograms, times U2, we just found it, 1282.59, minus mass A is 2 kilograms times U of A, 2793.7, minus mass B, 3 kilograms, times 1595.36. Now, when you do the math, you get that Q is minus 3960.53 kilojoules. Now, the minus sign means heat loss. Negative sign means heat loss. The system is losing heat during the process. Okay, problem 10. A frictionless piston cylinder device initially contains air at 200 kilopascals and the volume is also 0.2 meters cubed. At this state, a linear spring is touching the piston but exerts no force on it. The air is now heated to a final state of 0.5 meters cubed and 800 kilopascals. We are asked to find the work done by the air, the work done against the spring, and also showing it on a PV diagram. So what we have is a piston like this. So at the initial state, the piston is here, the spring is here, but there is no force involved, right? The spring is loose. At state 2, the piston is here and the spring is engaged. This problem is actually very, very easy. And there is only one point that you need to pay attention to, and that is every time there is a linear spring involved, pressure of the system has a linear relation with the volume of the system. So with that kept in mind, let's draw this entire process on a PV diagram. So this is my PV diagram. Okay. Now, initially, the system is at 200 kilopascals and 0.2 meters cubed. So we're here. Final state is 0.5 meters cubed, and the pressure is 800 kilopascals here. So we're looking at something like here. Now, as I said, during a process at which a linear spring is involved, pressure and volume have a linear relation. So there is a line going from state 1 to state 2. Now, the total work done by the air is the area under this curve. So we are looking at this area. Now, this is a geometry problem right now. The area is the work done from 1 to 2. Now, the area is 1/2 of 200 plus 800 times 0.5 minus 0.2. Work is 150 kilojoules. So the total area or the total work is 150 kilojoules. So this is part A. Now for part B, we are asked for the work done against the spring. Now, if there was no spring involved, we would have a constant pressure process, right? We would have a process like this. And this would be the work done during a constant pressure process. But because of the spring, we have this additional triangle here. Now this triangle is the work done against the spring. So the work against the spring, I'm going to show it with W of SP, is equal to the area of this triangle, which is 1/2 of 0.5 minus 0.2 times 800 minus 200, which, if we do the calculation, is 90 kilojoules. So 90 out of 150 kilojoules of the total work was against the spring. The rest was against whatever that was causing the constant pressure of 200 kilopascals. Okay, problem 11. We have a room, the volume is given 140 meters cubed, that is heated by an electric heater. Okay, now the heater is providing heat with a rate of 10,000 kilojoules per hour. A fan with a power of 100 watts is used to distribute the warm air inside the room. Okay, now we are approximating the heat loss rate of 5,000 kilojoules per hour from the room. Our initial temperature is 10 degrees Celsius. We want to raise it up to 20 degrees. How long would it take? Now, first of all, we are dealing with air, not steam anymore. So this is an ideal gas problem. And for ideal gas problems, for calculating the change of enthalpy and internal energy of ideal gases, we use specific heats at constant volume and constant pressure. So let's see what's happening. So we have this room. There is a fan on top distributing the air. And we have this heater that is providing 10,000 kilojoules per hour of heat, and we are approximating a heat loss of 5,000 kilojoules per hour. So the equation we're going to use is the first law. Q net minus W net is the change of energy of the system. Now for this problem, there is no kinetic and potential energy changes, so we are looking at the change of internal energy of the system. Now Q is Q dot times delta T. Q dot is the rate of heat transfer, delta T is the time. Now Q dot in our problem is Q dot in minus Q dot out. For us, it's 10,000 kilojoules coming in minus 5,000 kilojoules per hour going out, which gives us positive 5,000 kilojoules per hour. Now, kilojoule per hour is not a unit that we are comfortable with. We want to change kilojoules per hour to kilojoules per second, which is kilowatts. Now, how do we do that? So 5,000 kilojoules per hour, I can times this by 1 hour in the numerator over 3,600 seconds in the denominator. Now the numerator, hour, will cancel the hour here, and I will be left with kilojoules over seconds. So this is 1.39 kilojoules per second, which is 1.39 kilowatts. So Q is 1.39 delta T in kilojoules. Now I can do the same thing for work. Work is the rate of work times delta T. For our case, we only have 100 watts of fan work, which is 0.1 kilowatts times delta T. I can now plug in these two back into the equation. So I have 1.39 delta T plus 0.1 delta T is the change of internal energy, which is m U2 minus U1. Now we are dealing with air, and air can be treated as ideal gas, right? So if that's true, the change of internal energy of an ideal gas, or delta U, is CV, specific heat at constant volume, times T2 minus T1. Now here, CV of air is 0.718 kilojoules per kilogram Kelvin. Now you can read this from the tables, and I'm assuming the constant specific heats throughout the problems. So I can now write 1.49 delta T is equal to the mass of air times C of V, which is 0.718, times delta T, which is 20 minus 10. Now, because we are dealing with delta T, or difference between temperatures, it doesn't matter if you plug in Celsius or Kelvin. Just make sure that both temperatures are in the same scale. If one of them is Kelvin, the other one has to be Kelvin. If one of them is centigrade, the other one has to be in centigrade. Okay, so we now need to find the mass. How much air do we have inside this room? Now that's easy. Ideal gas equation says PV is equal to RT. Now, if I want to replace specific volume with volume, I get P volume is mass RT. So mass is P volume over RT. For our case, we can assume that the pressure inside the room is atmospheric pressure, so that will be 100 kilopascals times the volume is given 140 meters cubed over R. The gas constant for air is 0.287 kilojoules per kilogram Kelvin. Again, you can read it from tables. And the temperature, initial temperature is 10 degrees Celsius. So in Kelvin, that will be 283. From this little equation, we get that the mass of the air is 172.37 kilograms. So this is the mass. I can plug it into the blue equation to find delta T. So if I do that, and solve the equation for delta T, I get delta T is 830.6 seconds, which is about 14 minutes. So with the setup that we have with this heater, it takes about 15 minutes to raise the temperature from 10 degrees to 20 degrees Celsius inside this room. Okay, problem 12. We have an insulated rigid tank that is divided into two equal parts by a partition. Initially, one part has some air and the other part is evacuated. The partition is removed and the gas expands in the entire tank. Determine the final temperature and pressure in the tank. So this is the problem that we have. This is a tank. This is the partition. We have air on this side and vacuum on this side. And then the partition is suddenly removed. Remember, expansion against vacuum involves no work. So work is 0. The problem also says that the tank is insulated, so Q is 0. So if I write down the equation of Q minus W is delta U, these two both will be 0. And I end up with CV mass T2 minus T1 is equal to 0, which gives me T2 is equal to T1. So the final temperature is known. The final temperature is equal to the initial temperature. So T2 will be 50 degrees Celsius. Now let's move to the pressure. I'm going to use the ideal gas equation. I know that P1, specific volume 1 over temperature 1, is P2, specific volume 2 over T2. Now this gives me P2 is T2 over T1 times volume, specific volume 1 over specific volume 2 times P1. Okay, now because the temperature initial and final are the same, this goes, how about the specific volumes? The problem states that initially two sides of the tank were equal. So specific volume 2, which is the entire tank, is twice the specific volume 1, which is half the tank. This goes into 1/2. So P2 is P1 over 2. Plug in the numbers, P2 will be 400 kilopascals. So again, the only point that you need to pay attention to is that expansion against vacuum does not involve any kind of work. Also, because the tank was insulated, there was no Q involved, and you can readily conclude that the change of internal energy of the system is 0. For an ideal gas, that means the temperature does not change. So T1 is equal to T2. Now, ideal gas equation is in effect here. P1 V1 over T1 is P2 V2 over T2. Temperatures are equal, so you can drop them. Specific volume at state 2 is twice the specific volume of state 1 because initially the two parts were equal. That's all you need to know. The rest is just plug in numbers. Problem 13. Now we have 15 kilograms of air in a piston cylinder device, and we are heating it from 25 to 77 degrees by passing electric current through a heater. The pressure inside the cylinder remains constant at 300 kilopascals during the process, and 60 kilojoules of heat is lost. Determine the electric energy supplied in kilowatt hours. Okay, so we have this piston and cylinder like this. And we have an electric resistor here. And we are heating this up. So during the process, pressure remains constant. So it means that the piston is moving up. So we have boundary work here. Keep that in mind. Okay, so our equation is Q minus W is the change of internal energy. What is the Q? We only know that 60 kilojoules is lost. So Q is minus 60. How about W? W is the work out minus work in. Now work out, we are talking about expansion, so the system is doing work. So we are dealing with the boundary work, which for a constant pressure process is pressure times mass times V2 minus V1 minus the work of the electricity coming in, so work of electricity. So I'm going to plug them back up into the equation. I get minus 60 plus the electric work minus P mass volume 2 minus volume 1 is equal to mass U2 minus U1. I'm going to play with this equation a bit. I'm going to move this part of the equation to the right hand side. If I do that, I get electric work minus 60 is mass times U2 plus P specific volume 2 minus U1 plus P specific volume 1. Now this is a trick that we did a few problems before. By definition, this is enthalpy 1 and this is enthalpy 2. So my equation reduces to electric work minus 60 is mass times delta H of the system. Now for ideal gases, which is the case for us, we are dealing with air. For ideal gases, the change of enthalpy is Cp, specific heat at constant pressure, times delta T, T2 minus T1. So this is the thing that we are going to use. Cp for air at this range of temperature is 1.005 kilojoules per kilogram Kelvin. Okay, now keep that in mind. Now if I continue, I get the electric work minus 60 kilojoules of heat loss is equal to the mass, 15 kilograms, times Cp, 1.005, times delta T, which is 77 minus 25. Now you do the calculations, you get that the electric heater work is 843.9 kilojoules. Okay, but this is not the unit that the problem asks. Problem explicitly asks for kilowatt hours. Kilowatt hours is a unit for energy, not power. It has watts in it, but because it's timed by a unit of time, it gives you energy. So I want to convert kilojoules to kilowatt hours. How do I do it? Now a kilojoule is a kilowatt times 1 second. I can times this by 1 hour over 3,600 seconds. Now 1 hour over 3,600 seconds is 1 over 1 because 1 hour is 3,600 seconds. So seconds cancel each other and we are left with this conversion rate. 1 kilojoule is 1 over 3,600 kilowatts hours. So that means 843.9 kilojoules is 843.9 over 3,600 kilowatts hours, which gives us the electric work is about 0.234 kilowatts hours. Now, if you're paying electric bills, you would notice that the price you're paying is for unit kilowatt hours. So kilowatt hours is a very common energy unit when electric power consumption is involved. This problem had a constant pressure process, so you need to pay attention to the boundary work when you are dealing with the constant pressure process. Now, the boundary work, we did a trick and included it into the right-hand side of the equation. We changed the internal energy of the system into the change of enthalpy of the system. So we took care of the boundary work. That's why we didn't include it with the rest of the works. Then we had 60 kilojoules of heat going out into the waste, and the rest is all electric work. We just plugged in numbers. We found it in kilojoules. The unit we are asked is kilowatt hours, so we made a conversion and use that conversion to find the energy in kilowatt hours. Okay, problem 14. We have stainless steel ball bearings. The density and specific heat are given, and the diameters of individual balls are also mentioned. We want to quench them in water at a rate of 800 per minute. The balls leave the oven at a uniform temperature of 900 degrees and then are exposed to air at 25 degrees for a while before they are dropped into water. If the temperature of the balls drop from 900 to 850 prior to quenching, determine the rate of heat transferred between the balls and air. So although it's a quenching with water system, we are not really interested in the water. We just want to know how much heat is transferred to air. So for each ball, Q minus W is equal to change of internal energy. There is no work involved, so we can drop the work term and then say Q is M U2 minus U1. Now these balls are solids, so we can find the change of internal energy of solids using specific heats. This is MC T2 minus T1. Okay, temperature initial and temperature final are given. We just need to find the mass of each ball. So the mass of each ball is density times the volume of individual ball. That would be density times the volume. Volume of a ball, spherical ball, is pi 4 over 3, diameter over 2 to the power of 3. That will give us, the density is 8085 times pi times 4 over 3 times the diameter is 1.2 centimeters, which is 1.2 times 10 to minus 2 meters, or 2 to the power of 3. Now if you do that, you get that the mass of individual balls are 0.0073 kilograms, or about 7 grams. So each ball has this mass. For an individual ball, Q is mass 0.0073 times C, it's given 0.48, times delta T, which is 850 minus 900. This is equal to 175 kilojoules. So each individual ball loses 0.175 kilojoules of energy to air. Now the minus sign shows that the ball is losing heat. But we are looking for the rate, and we also have this number, 800 balls per minute are getting cooled down. So total Q, or the Q dot, is 800 balls per minute times Q of a single ball, which gives you minus 140 kilojoules per minute. Now, kilojoules per minute is not good for us, so I'm going to change it to kilowatts. In order to do that, I'm going to say 1 minute is 60 seconds. And so Q dot is minus 2.34 kilowatts. So this was a very simple problem. We were dealing with a solid. Now, when dealing with solids, the change of internal energy of a solid can be written as C times delta T. Okay, that's the only point in this problem. We found the individual ball heat loss minus 0.175 kilojoules of energy was lost from the ball to air, individual ball to air, that we knew that 800 balls were cooling down per minute. So I just multiplied 800 balls per minute times the Q loss of an individual ball and found that the rate of heat transfer to air is 2.34 kilowatts. Okay, the final problem. Now we have an iron, it's 1000 watts. The plate, the base plate of this iron is 0.5 centimeter thick aluminum. The surface area of the space is given, and we are assuming that 85% of the power input of the iron goes directly into heating the plate. We want to know how long it takes for the iron plate to reach the temperature of 140 degrees Celsius. So it is very easy. I'm going to say Q minus W is the change of internal energy. Now for a solid, change of internal energy can be written as mass times C delta T. So we need to find the mass. Mass is density times volume. I can say the mass is 2,770 times thickness is 0.5 centimeters, which is this much meters, times the surface area, which is 0.03 meters squared, and you get that the mass is 0.4155 kilograms. Okay, so we found the mass. We can continue. So Q, 85% of 1,000 watts input, which by the way is 1 kilowatts input, is going into the heat. And that is the power. In order to find the actual energy, you have to time it, you have to multiply it by time. So it is 0.85 times 1 times delta T. There is no work involved. This guy is gone. Is equal to, the mass is 0.4155 times the C is 0.875 times 140 degrees minus the initial temperature 2020. Now if you do the math, we need 50.47 seconds for the iron to reach the temperature of 140 degrees Celsius. Now again, this was a very easy problem. I just wanted you to get a feeling of what to do with a solid or a liquid. Now, if you're dealing with solids and liquids and you want to find the change of internal energy and change of enthalpy, you can use the equation mc delta T, okay? Thank you for staying to the end of yet another video. If you find this video helpful, please give it a like as it greatly helps the channel. Also, please consider subscribing for more science and engineering content. Thanks again and see you in another video.